Combinatorics, Lecture 10, Recursive Sequences. We start with a motivating example. Let us recall the classical Fibonacci sequence, which looks as follows. So it goes 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and so on. Here, the first term of the sequence is 0, the second term is 1, and then each next term is the sum of the two previous terms. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on. The phenomenon that the next term of a sequence depends in a certain fixed way on the previous terms is called recurrence. And the question which we would like to ask is it possible to give an explicit formula for elements in a recursive sequence? So, for example, we will show later that the nth term of the Fibonacci sequence equals the following thing: 1 divided by the square root of 5 times the following expression: 1 plus square root of 5 divided by 2 to the power n minus 1 minus square root of 5 divided by 2 to the power n. And here, of course, there are many questions. The first question would be, why on earth should a square root of 5 appear for the Fibonacci sequence? And this is exactly what we are going to discuss and answer in this lecture. So let's start with just the general definition of a sequence. So for simplicity, we will work over the field C of complex numbers. Definition: a sequence of complex numbers is a map from the set of all non-negative integers to the complex numbers. So the usual notation is that we have a sequence A. That's the sequence which is given by A0, A1, A2, and so on. So it's denoted as a collection of AI, where I is a non-negative integer, and AI is the value of our sequence at the non-negative integer I. Sometimes it's convenient to consider maps from positive integers to the complex numbers, or more generally from all integers that are greater than or equal to a fixed integer k. And in such case, we write that a is equal to ai where I is a positive integer, or ai where I is an integer greater than or equal to k. Or sometimes one can even write that the sequence A consists of ai where I is greater than 0, and we understand here that I is an integer in this notation for the sequence, and so on. For example, we have a sequence ai is equal to I for all I greater than or equal to 0. Example 2, we have a sequence ai is equal to the cosine of I for all I greater than or equal to 0. That's a complicated sequence. Of special interest for combinatorics are the so-called constant recursive sequences. Definition: a sequence A is called constant recursive provided that there exists a positive integer k and complex numbers gamma 1, gamma 2, and so on gamma k, such that the term an in the sequence equals gamma 1 times an minus 1 plus gamma 2 times an minus 2 plus and so on plus gamma k a n minus k for all n that are greater than or equal to k. And this equation is called the linear recurrence with constant coefficients. For example, the Fibonacci sequence which we started with, that's a sequence of numbers which are usually denoted f sub n, where n is a non-negative integer. This is a constant recursive sequence because by definition fn is equal to fn minus 1 plus fn minus 2 for all n greater than or equal to 2. So here we have k is equal to 2 and gamma 1 and gamma 2 are equal both to 1. Example 2. The sequence given as follows, so ai is equal to 2 to the power I, where I is a non-negative integer, is also constant recursive, because here ai is equal to 2 times ai minus 1 for any I greater than or equal to 1. So we have k is equal to 1 and gamma 1 is equal to 2. Here is a more complicated example. The sequence bi, which is equal to I for all I greater than or equal to 0, so the identity map, so to say, is constant recursive because here bi is equal to 2 times bi minus 1 minus bi minus 2 for all I greater than or equal to 2. So we can take k to be equal to 2, gamma 1 to be 2, and gamma 2 to be minus 1. Here are some basic properties of constant recursive sequences. Property 1. If we know that some sequence A is constant recursive with parameters k and gamma 1, gamma 2, and so on, gamma k, then the knowledge of A0, A1, and so on, ak minus 1 uniquely determines all other elements of the sequence. Because if we know these elements, we can use the recurrence to compute the element ak. If we know A1 and so on, ak, we can use the recurrence to compute ak plus 1, and so on. Corollary, the map phi, which takes as input a constant recursive sequence with parameters k, gamma 1, gamma 2, and so on, gamma k, and maps it to the collection of initial elements a0 and 1 and so on, ak minus 1, is a bijection between the set of all constant recursive sequences with parameters k, gamma 1, gamma 2, and so on, gamma k, and the vector space C to the power k. Lemma: the set of all sequences is a vector space over the complex numbers with respect to the pointwise addition and multiplication with scalars. So this is the usual statement that if we take all maps into a vector space, so the set of these maps has the structure of a vector space. Remark: the map phi is a linear map. So we will prove this, that phi is a linear map. In other words, if both A and B are two constant recursive sequences with fixed parameters k and gamma 1, gamma 2, and so on, gamma k, so here the point that the parameters should be the same for both A and B, then the sum of A and B, which is the sequence consisting of AI plus BI, and the sequence lambda AI, so lambda A, where lambda is a fixed scalar, both the sequences are constant recursive with the same parameters. So let's prove this. Assume that an is equal to gamma 1 an minus 1 plus and so on plus gamma k an minus k. So A is a constant recursive sequence with parameters k, gamma 1, gamma 2, and so on. And similarly assumes that B is also constant recursive with the same parameters. Then we can compute an plus bn, and we can use these recurrences to write that this is equal to gamma 1 an minus 1 plus and so on plus gamma k an minus k plus gamma 1 bn minus 1 plus and so on plus gamma k bn minus k. And now we can rearrange this and rewrite it as gamma 1 times an minus 1 plus bn minus 1 plus and so on plus gamma k times an minus k plus bn minus k. But this means exactly that the sequence A plus B is also constant recursive with the same parameters. Similarly, if we consider lambda times A, so lambda times an, using our recurrence, can be written as lambda times gamma 1 an minus 1 plus and so on plus gamma k an minus k. And again, we can rearrange this expression into gamma 1 times lambda an minus 1 plus and so on plus gamma k times lambda an minus k, which exactly shows that lambda times A is also constant recursive with the same parameters. The parameter k in a constant recursive sequence is usually called the order of the recurrence. If we have a constant recursive sequence of order 1, this means that an is equal to gamma an minus 1 for all n greater than or equal to 1, where gamma is a fixed complex number. Proposition: if A is a constant recursive sequence with recurrence of order 1 and parameter gamma, then an is equal to a0 times gamma to the power n for all n greater than or equal to 1. Proof. Let's proceed by induction on n. For n is equal to 1, we have a1 is equal to gamma to the power 1, a0 that's directly follows from our recurrence. If n is greater than 1, then from the recurrence we have that an is equal to gamma times an minus 1. But by the inductive assumption, an minus 1 equals gamma to the power n minus 1 times a0, and now we can collect this all together and get gamma to the power n times a0. And this completes our proof. Next, we will talk about the characteristic polynomial of recursion. So let A be a constant recursive sequence with recurrence of order k and parameters gamma 1 and so on gamma k. Definition: the polynomial x to the power k minus gamma 1 x to the power k minus 1 minus gamma 2 x to the power k minus 2 minus and so on minus gamma k is called the characteristic polynomial of the recurrence. For example, the characteristic polynomial for the Fibonacci recurrence is x squared minus x minus 1. This is because fn is equal to fn minus 1 plus fn minus 2. Example 2, the characteristic polynomial for the order 1 recurrence with parameter gamma is x minus gamma. That's because ai is equal to gamma ai minus 1. Example 3, the characteristic polynomial for the identity sequence 0, 1, 2, 3, and so on, we have already seen that this sequence corresponds to the recurrence an is equal to 2 times an minus 1 minus an minus 2. So then the characteristic polynomial is x squared minus 2x plus 1, which is, by the way, x minus 1 squared. Characteristic polynomial is a very important tool in studying constant recursive sequences. In particular, roots of the characteristic polynomial have very interesting properties. Proposition: let f of x, which is equal to x to the power k minus gamma 1 x to the power k minus 1 minus and so on minus gamma k, be the characteristic polynomial of some recurrence. Let lambda be a root of this polynomial. Then, for each complex number c, the sequence c times lambda to the power n, where n is greater than or equal to 0, satisfies our recurrence. Which means that c lambda to the power n equals gamma 1 c lambda to the power n minus 1, plus and so on, plus gamma k c lambda to the power n minus k for all n greater than or equal to k. Proof: we can rewrite this condition for the recurrence in the following way. We move everything to the left-hand side and pull out of the bracket c and lambda to the power n minus k. So then we will get the expression lambda to the power k minus gamma 1 lambda to the power k minus 1 minus and so on minus gamma k. Then this expression times c times lambda to the power n minus k is equal to 0. And since lambda was the root of the characteristic polynomial, we see that the first factor in this expression is actually the evaluation of our characteristic polynomial at lambda. By our assumption, this is 0, which means that our expression is an identity. The left-hand side is indeed 0. And this proves our proposition. But this observation has the following corollary. So, theorem: let f be the characteristic polynomial of some recurrence. So f is of the form x to the power k minus gamma 1 x to the power k minus 1 minus and so on minus gamma k. Assume that this polynomial has different roots. So we have lambda 1, lambda 2, and so on lambda k, pairwise different elements, and all are roots of f of x. Let A be a sequence which satisfies this recurrence. Then there are unique complex numbers alpha 1 and so on alpha k, such that for all non-negative I, the term ai of our sequence equals alpha 1 times lambda 1 to the power I, plus and so on, plus alpha k times lambda k to the power I. So this gives us a very explicit general formula for all terms of our sequence. Let us also note that we have chosen to work over the complex numbers, That's an algebraically closed field, so over the complex numbers, any polynomial of degree k has exactly k roots. However, sometimes in the degenerate cases, some of these roots may coincide with each other. So we formulated the theorem in the so-called generic case, where all roots are different. Proof. Let V be the vector space of all sequences that satisfy our recurrence. We already seen that the map phi, which we saw in the beginning of the lecture, is a linear isomorphism between this vector space V and the standard vector space C to the power k. So in particular, this means that V has dimension k, because C to the power k has dimension k. From the previous proposition, we know that if we take the root lambda I of our characteristic polynomial, and consider the corresponding geometric sequence lambda I to the power n, where n is a non-negative integer, this geometric series belongs to V. And from the van der Monde determinant, we know that different geometric series are linearly independent. But this means that we have k linearly independent elements in a k-dimensional space. So here we use that all roots of our characteristic polynomial are different, so the corresponding geometric series are also different and also linearly independent. And now the claim of our theorem simply restates the fact that if you have a vector space, then any element of the vector space can be uniquely written as a linear combination of the elements of the basis. So we have a vector space of dimension k. In that vector space, we have k linearly independent elements, so these are geometric series which correspond to roots. So they must form a basis because the number is k is the dimension, and so any other element of the vector space, any other sequence with the same recurrence, should be a linear combination of these basis elements. That's our theorem. Now we can apply it to the Fibonacci sequence. So recall that we have the Fibonacci sequence, which has the recurrence fn is equal to fn minus 1 plus fn minus 2, where f0 is 0 and f1 is 1. So the characteristic polynomial of this recurrence is x squared minus x minus 1, directly from here. And this one has two different roots, 1 plus minus root of 5 divided by 2. So here is how root of 5 appears for the Fibonacci sequence. It appears as a part of the root of the characteristic polynomial. Consequently, from our theorem, we know that the nth term of our sequence, fn, must be equal some complex number alpha times 1 plus the square root of 5 divided by 2 to the power n, and then plus some complex number beta times 1 minus the square root of 5 divided by 2 to the power n. To determine alpha and beta, we use our initial conditions that f0 is 0 and f1 is 1. So this gives us two equations. So f0 is 0 gives us the equations that alpha plus beta is 0, and f1 is equal to 1 gives us that alpha times 1 plus the square root of 5 divided by 2 plus beta times 1 minus the square root of 5 divided by 2 is equal to 1. And the unique solution to the system is alpha is equal to 1 divided by the square root of 5, and beta is equal to minus 1 divided by the square root of 5. Therefore, we can write fn as 1 divided by the square root of 5 times 1 plus the square root of 5 divided by 2 to the power n minus 1 minus the square root of 5 divided by 2 to the power n. And this is true for all n greater than or equal to 0. Let us now also describe the theorem in the general case. So assume that we have a characteristic polynomial f of x of some recurrence, and assume that f of x decomposes into linear factors in the following way. So f of x is equal to x minus lambda 1 to the power m1 times x minus lambda 2 to the power m2 times and so on, times x minus lambda r to the power mr, where lambda i's are pairwise different. Then the following sequences form a basis in the space of all sequences with this recurrence. So the sequences will be indexed by pairs s, j, where s is a number between 1 and r, so that corresponds to a root of our polynomial, And j is a number between 0 and ms minus 1. So that corresponds to the multiplicity of this root. So we can vary j between 0 and the multiplicity of the root minus 1. So for a fixed s and j here, we take the sequence which is given by n to the power j times lambda sub s to the power n, where n is a non-negative integer. So note that the degree k of our polynomial equals m1 plus m2 plus and so on plus mr, so the total number of elements here is exactly k. So we really have a k-dimensional vector space, and here we have a basis there consisting of k elements. And also, if all mi's are equal to 1, then r is equal to k, of course, and then the sequences above, so all ms are equal to 1, so j can only be 0, and so the first term disappears, and we only get the geometric series which correspond to roots. That was exactly our previous theorem. Here is an example. Consider the sequence, the identity sequence where ai is equal to I or an is equal to n, where n is greater than or equal to 0. So we know that it satisfies the recurrence an is equal to 2 times an minus 1 minus an minus 2. The initial conditions are a0 is 0 and a1 is 1. The characteristic polynomial we already computed. It was x minus 1 to the power 2. So now we have one root of multiplicity 2. So this means that the general sequence for this recurrence has the form alpha times the root of the polynomial 1 to the power n plus beta times n times 1 to the power n. Of course, 1 to the power n disappears, so 1 to the power n is 1. So the general sequence for this recurrence has the form alpha plus beta n for some alpha beta complex numbers. And now we can use the conditions that alpha 0 is 0 and alpha 1 is 1. So this gives us alpha is equal to 0 and alpha plus beta is equal to 1. And so an is equal to 0 plus 1 times n, which is n for n greater than or equal to 0. And so we, in this way, come back to our original sequence, so we see how the whole theory works in this example. Let's now discuss an application of this theory. Let us compute for n greater than or equal to 1 the n times n determinant of the following form. So we have the n times n matrix, where the main diagonal consists of 1s, the diagonal just above and just below it, they also consist of 1s, and the rest is 0. That's usually called the tri-diagonal matrix. Let's denote its determinant by d sub n. Let's try to compute this d sub n. We can expand this determinant along the last row, and this will give us the recurrence d sub n is equal to d sub n minus 1 minus d sub n minus 2. Here's the illustration for n is equal to 5, but it works for any other n in the same way. So when we expand with respect to the last row, there will be only two non-zero summons, because we only have here 1 and 1, and the rest is 0. The summand for the diagonal element will have sign plus, and when we delete last row and last column, we just get dn minus 1 on the nose. When we delete the last row and the penultimate column, we will have such a determinant. Now it will also have sign minus because it's next to the sign plus thing. And then in this determinant we see that we have here 1, and then here the block diagonal element which corresponds to dn minus 2. That's a block diagonal matrix. Here we only have 0, so the determinant of this matrix is equal to the determinant of this matrix, which is 1, times the determinant of this TL matrix, which is dn minus 2. This gives us our recurrence. So our sequence dn is constant recursive of order 2, and the initial values are d1 is equal to 1 and d2 is equal to 0. We can actually extend it to the index 0 by setting d0 to be equal to 1, and so we keep the recurrence. So d2 becomes d1 minus d0 as well. So we can assume that our sequence starts from 0 and the initial element d0 is 1. So the recurrence is dn is equal to dn minus 1 minus dn minus 2 for all n greater than or equal to 0, and the initial values are d0 and d1 are equal to 1. The characteristic polynomial is x squared minus x plus 1, and this one has two different roots, 1 plus minus I square root of 3 divided by 2. So here I is the imaginary unit, the complex number, and so we see here, so it was important that we work over the complex numbers because we can have very small polynomials which only have complex roots. This polynomial doesn't have any real roots. And so from our general theory, dn is equal to alpha times one of the roots of this polynomial to the power n plus beta times the other root to the power n for all n greater than or equal to 0. To determine alpha and beta, we use the conditions d0 and d1 are equal to 1. So the first condition gives us alpha plus beta is equal to 1, and the second condition gives us alpha times the first root plus beta times the second root is equal to 1. The solutions are alpha is equal to 1/2 minus I divided by 2 square roots of 3, and beta is equal to 1/2 plus I divided by 2 square roots of 3. And so for n greater than or equal to 0, dn is given by the following expression, 1/2 minus I divided by 2 square roots of 3, and then times 1 plus I square root of 3 divided by 2 to the power n, plus 1/2 plus I divided by 2 square roots of 3 times 1 minus I square root of 3 divided by 2 to the power n. And that's our answer. And again, it's important to emphasize that we need complex numbers to write this formula. Here is another example. Let us determine a general formula for the nth term of the sequence A, which satisfies the recurrence an is equal to 3 times an minus 1 minus 3 times an minus 2 plus an minus 3, this should be 3, and the initial values are a0 is equal to a2 is equal to 0, and a1 is 1. This is a linear recurrence of order 3. The characteristic polynomial is x to the power 3 minus 3x to the power 2 plus 3x minus 1, which is x minus 1 to the power 3. So we have only one root, 1, and it has multiplicity 3. This means that the general form of our sequence an is alpha plus beta n plus gamma n squared for some alpha, beta, and gamma complex numbers. The initial conditions where a0 and a2 are equal to 0 and a1 is equal to 1 give us the equations alpha is equal to 0, alpha plus beta plus gamma is equal to 1, and alpha plus 2 beta plus 4 gamma is equal to 0. And the unique solution of this is alpha is equal to 0, beta is equal to 2, and gamma is equal to minus 1. And this means that our sequence an is given by 2n minus n squared for all n greater than or equal to 0. Let us do one more exercise which involves the Fibonacci sequence. So let fn be the Fibonacci sequence. Prove that f0 plus f1 plus and so on plus fn is equal to fn plus 2 minus 1 for all n. Solution. Let's first check this formula. So our sequence starts as follows: 0, 1, 1, 2, 3, 5, 8, 13, and so on. Let's check this identity for small n. For n is equal to 0, we have 0 is equal to 1 minus 1. It works. For n is equal to 1, we have 0 plus 1 is equal to 2 minus 1. Also works. For n is equal to 2, we have 0 plus 1 plus 1 is equal to 3 minus 1. Works. For n is equal to 3, 0 plus 1 plus 1 plus 2 is equal to 5 minus 1. Also works, so this looks okay. Let's try to prove it using induction on n. So we already checked the basis of the induction, we did the small cases. And to prove the induction step, consider f0 plus f1 plus and so on plus fn plus fn plus 1. And now here we can use inductive assumption to rewrite the sum of the first n elements as fn plus 2 minus 1. So the whole thing becomes fn plus 2 minus 1 plus fn plus 1. But now using the Fibonacci recurrence, fn plus 1 plus fn plus 2 is equal to fn plus 3. and then the whole thing becomes fn plus 3 minus 1. And that's exactly what we needed to prove. Some additional problems and questions at the end. Problem question 1. Check with all details that the map phi from the set of all constant recursive sequences with fixed parameters k and gamma 1 and so on gamma k to c to the power k is linear. Problem question 2. Prove with all details the theorem about the general case of linear recurrence. Problem question 3. Prove that the determinant sequence dn, which we studied during the lecture, is actually periodic with period 6. Problem question 4. Determine a formula for the general term of a sequence given by the recurrence an is equal to 2 times an minus 1 minus an minus 2, and with the initial values a0 is equal to 1 and a1 is equal to 2. And problem question 5. Let fn be the Fibonacci sequence. Prove that f1 plus f3 plus f5 plus and so on plus f with the index 2n minus 1 is equal to f to n for any n. Thank you very much and see you next time.